Alright, so now we move on to our next topic, which is graphical method of solution of a pair of linear equations. We won't jump right into it because I'll tell you about a few things first. Okay, so first understand, I told you we are dealing with a pair of linear equations. By now you're very well versed with this term, but I'm sure you might be wondering what exactly are we referring to as the solution of the system. So by solution, we could mean the algebraic solution or the graphical solution. Essentially both are the same, but I'll tell you about both of them. So first let's talk of algebraic solution. So algebraic solution is like I give you two equations, or maybe just one equation, like I give you 2x plus 2y equal to 0. Now what values of x and y would satisfy that equation? That is the algebraic solution. Like in this case, if I say x is equal to 0 and y is equal to 0, your equation boils down to 2 into 0 plus 2 into 0 equal to 0, 0 equal to 0, which is LHS equal to RHS. Now LHS here means left hand side and RHS means right hand side, as in the left hand side of the equal to and right hand side of the equal to. So now we see that this value of x and this value of y, together they are satisfying this equation, that is LHS and RHS are turning out to be equal. That is what we call the algebraic solution of an equation. Now when I am referring to the graphical solution, you know that we are dealing with a pair of linear equations. So I expect to have two straight lines on my graph sheet. Now wherever these two straight lines are going to touch each other, they are going to meet each other, that point of contact is the solution when we are talking about it graphically. Okay, so we have a pair of linear equations. By solution we could mean algebraic or graphical, just like we had two representations for a pair of linear equations, algebraic and graphical. So for the algebraic solution, we are referring to those x and y values which on insertion in an equation give me LHS equal to RHS, or in other words they satisfy the equation. And by graphical solution, I mean the points where the two straight lines are meeting each other. With that knowledge in mind, let's look at the three possibilities. I told you earlier also that there are three possibilities. We can have intersecting lines, coinciding lines, or parallel lines. And I told you at that time that we'll just discuss them in detail very soon. So now's the time. So first is intersecting lines. Intersecting lines, just like a pair of scissors, they meet at a common point. And that is just one, okay? They meet only at one point, and that point would obviously mean the graphical solution. I just told you, wherever the two lines meet, that is the graphical solution. So this point of contact will give me unique solution. It's interesting to see why we are calling it unique. Unique means just one of its kind, and that is so in this case because there's only one point of contact. Okay, so all you need to remember is that in intersecting lines there is only one point of contact, which corresponds to the unique solution for that pair of linear equations in two variables. Moving on to the next case, coincident lines. Now if we are dealing with a pair of linear equations, we expect to have two straight lines on the graph sheet, but here we are having one. It's just an illusion. We are actually having two straight lines, but they're stacked one over the other. Like we had it in that case where we were talking about two friends who visited a stationery shop, Romila and Sonali. So they essentially have the same equation, as a result of which we have only one single straight line. And coincident, as the name suggests, we are having two straight lines and they're coinciding with each other. Now if I want to find out their graphical solution, I need to look for the points of contact. And here, since they're completely eclipsed one over the other, it means that they are meeting each other at almost every possible point. So there are infinite points of contact, and hence here for coinciding lines, you will get infinitely many solutions. Okay, so we'll have infinite solutions here due to infinite points of contact. Okay, so two straight lines stacked one over the other. Okay, now I'll give you some examples also. So for intersecting lines, I'll give you some equations. You may consider this as your homework. Intersecting lines and coincident lines. This homework is very doable, don't worry, okay? So for intersecting lines, I'll give you two equations. Let me give you 3x minus y is equal to 5 as the first equation and x plus y is equal to 1 as the second equation. For coincident lines, it is x minus 2y equal to 2 and 4x minus 8y equal to 8. Okay, now this is very doable because you already know how to graphically represent a pair of linear equations. We've discussed some examples also earlier. So make use of those examples and that knowledge and you'll plot it and then you'll see if you get a graph like this or if you get just a single straight line. Okay. Now moving on to the last case, which is that of parallel lines. So parallel lines, as you know in geometry, they never meet. So you can get them like this, like this, like this, like this. Any which way, but they'll never meet. So here if they're never meeting, there'll be no point of contact. Okay. No point of contact, which means there will be no solution. Okay, so here parallel lines give us no solution. Okay, I'll give you some example here, like again a homework actually. So take these two equations from me, 2x minus y equal to minus 3 and 2x minus y equal to 4. Try to plot them on a graph sheet and tell me if you get parallel lines or what. Okay, so you know how to do it graphically, right? So I hope you'll be able to do it. Then we have consistent and inconsistent systems. So first of all, let's understand what we are referring to as a system. The system refers to a set of equations. Okay, but the only catch here is that they should be in the same variables. Okay, so if I give you an equation like 2x plus y is equal to 3a. So this is just a system of one equation. And if I give you 4x plus 2y is equal to 8. Now this is a system of two equations because both of them are also having the same variable. So like this, I can have n number of equations and I'll get a system of n equations. Okay, so this is a system. Now on the basis of solution, the system can be categorized into consistent and inconsistent systems on the basis of the solution. We now know what a solution means, right? It could be algebraic, it could be graphical. So we have consistent and inconsistent systems. So what do we mean by a consistent system? It is one which gives us at least one solution. At least one solution. And inconsistent system is one which gives us no solution. Okay. Now what do we mean by at least one? It means greater than or equal to 1. That means minimum 1. 1 is definitely going to be there. But you can even have more than one solutions. So we've discussed three types of equations, like three types of lines actually on a graph sheet: intersecting, coinciding and parallel. So which type of line would fall into which category? Let's look at that very soon. So basically, like if I give you intersecting lines, here you have just one solution, so that is the unique solution. So intersecting lines would fall into the consistent system. If I give you coinciding lines, they have infinitely many solutions, so definitely a consistent system. Parallel lines would be an inconsistent system because the render is no solution. Okay. Now when we talk of consistent and inconsistent systems, we also talk of dependent and independent pair of linear equations. Okay, I'll just tell you what that means. So dependent and independent. So I'll tell you, so if I'm having a system, just you can make use of this flow chart to understand it better. So on the basis of solution, what types of systems can we have? Consistent and inconsistent. And further, I told you consistent could be intersecting. Okay, intersecting unique solution, only one point of contact, or coinciding, infinitely many solutions because infinitely many points are there of contact. Okay, then I told you inconsistent is the one which gives us no solution, so here I told you parallel lines. Now further, this consistent system could be dependent, like coinciding lines are a dependent system and intersecting lines are independent. Now what do we mean by dependent? So in coinciding lines, whenever you come across any case of coinciding lines, you will notice that if my first equation is like x minus 2y equal to 0, then the second equation will always be a multiple of the first equation only, which makes it dependent on the first equation. So say if I multiply this equation by 2, I will get 2x minus 4y equal to 0. And now this becomes a consistent system, but it is coinciding and dependent. Dependent because the formation of this equation number 2 depends on the first equation, which when multiplied by a suitable factor would give me this equation. So instead of multiplication by 2, I can multiply it by 3, by 4, by any constant, okay? So that is why we call it dependent. Okay, you must be seeing Romila and Sonali's case. Go back to that case and you'll see that the equation which we got for Sonali was exactly twice of what we got for Romila. And that's why we got a single straight line. That was actually a case of coinciding lines, okay? So that is what we mean by dependent. Formation of one equation depending on the existence of another equation. Now, consistent and inconsistent systems like intersecting, parallel, coinciding lines, we can figure that out graphically very easily. But guess what? We can even do that algebraically. So this is the algebraic way of doing it. You just look at the equations and you get to know. So for that, you need to refer to the general equation, the general form of an equation. So I told you in the very beginning that this is the general form of a linear equation, two variables, ax plus by plus c equal to 0. Now, this chapter is all about pair of linear equations. So I need to consider one more equation. So let me make these constants as a1, b1, c1, and this is my equation number 1. And let's say my second equation is a2x plus b2y plus c2 is equal to 0. Now what you need to do is, you need to take these ratios a1 by a2, b1 by b2 and c1 by c2, and then you have to compare their values and you'll get to know if the system is consistent or inconsistent, and further if it is intersecting, coinciding or parallel. So let me take this first system. So here compare this with the first equation over here. So you'll get to know that a1 is 1, b1 is minus 2, c1 is 0. Compare this with this equation over here. So you'll get a2 as 3, b2 as 4, c2 as minus 20. What next? Quickly calculate a1 by a2. That will be 1 upon minus 2. Oh, sorry. It will be 1 upon 3. Then b1 upon b2, which will be minus 2 upon 4, c1 upon c2, which will be 0 upon minus 20. Now here, this itself will tell you, okay, that a1 by a2 is not equal to b1 by b2. When this is the case, we get intersecting lines. So that's how we make out if a pair of equations is going to render me intersecting lines. So you just need to look for these ratios, and a1 by a2 and b1 by b2 won't be equal. I'll just solve one more case for you. So again, compare this equation with the first equation over here. Compare this with the second equation over here. And let's see who writes a1, b1, c1 and all first. Okay. Let's compete together. Okay. Okay. Time's up. So a1 is 2, b1 is 3, c1 is minus 9, a2 is 4, b2 is 6, c2 is minus 18. Let's write these. a1 by a2 is 2 by 4, b1 by b2 is 3 by 6, c1 by c2 is minus 9 by minus 18. If you further, solve these fractions, you simplify them, you'll realize that all these ratios are turning out to be equal. So a1 by a2 is turning out to be equal to b1 by b2 and c1 by c2, because all of them are equal to 1 by 2 only. So such a case gives me a pair of coinciding lines. Similarly, you can solve for parallel lines also. Find out these ratios of a1 by a2, b1 by b2, c1 by c2. And for parallel lines, you will realize that a1 by a2 and b1 by b2 are equal, but they are not equal to c1 by c2. Okay. So graphically we saw how we can figure it out. Now algebraically also we are through with it. Let's summarize it here. So you find these ratios and then you compare them. So when a1 by a2 and b1 by b2 are not equal, you get intersecting lines which always give us one solution, which we call unique. Then for coinciding lines, you get a1 by a2 equal to b1 by b2 equal to c1 by c2. So that gives me infinitely many solutions. Then a1 by a2, b1 by b2 are equal, but c1 by c2 is not equal. So we get a case of parallel lines, no solution. Now what is the use of figuring it out algebraically? So the interesting thing is that whenever you just look at an equation, you'll be able to make out its graph. Like you obviously know you're going to get a pair of straight lines, but you'll be able to predict just by looking at the equations, and then your classmates will be wondering like, how can you do that without even plotting it on a piece of graph? So That's how. So that's like magic then, okay, to them. So you can figure that out algebraically and make predictions for its graphical interpretation. So this is again a summary. This is an important point that the converse is true for any pair of lines. So if I ask you to prove that any two equations are non-intersecting, then you just have to prove that a1 by a2 and b1 by b2 are equal. If I have to prove they are non-coinciding, you can prove that these ratios are not equal to one another. In case of parallel, you will prove that these two ratios are not equal, but these two ratios are equal. Okay. Now let's understand this by means of some examples. So check graphically whether the pair of equations is consistent. So first of all, for this you'll need graphical representation. So let's quickly do that. Let's write the equations. X plus 3y equal to 6. You already know how to represent it geometrically. So yeah, you might be wondering why again and again I'm calling this graphical representation geometrical. It's not the normal geometry which you do, with compass and protractors. It's actually referring to coordinate geometry, okay, where you deal with plotting of points and all. That's when. Okay, then yeah, what do? We make chocolate bars. Let's make one for equation number 1. Let's make one for equation number 2. How do we slice them? One horizontal line, and then how many vertical lines? 3. 1, 2, 3. Let's fill them in x and y, the two variables. Now again you can show the entire working like we did earlier. So if I take x to be 0, I'll get y equal to 2. I hope you know that I'm referring to this equation number 1 right now. If I take this as 3, I'll get 3 plus 3y as 6, 3y as 3, which is 1. And then if I take this as 6, 6 and 6 cancel, I'll get 0 over here. Then here again I can do it. So if I take x as 0, I'll get y as minus 4. I'm referring to equation number 2 right now. And if I take x as 3, I'll get this as minus 2. If I take this as 6, I'll get this as 0. Time to plot these points. So this is 0, 2. Label it also. 3, 1. 6, 0. Now this should be like cakewalk for you all because we've done this already. Then we have 3 minus 2. The only thing that we have not yet practiced is how to find out the solution graphically, and that's why we've taken this example. Now what you have to do is you have to join these points and join these points. You will get two straight lines. Okay, so this is the point where they are meeting. Now I hope what you're doing over here is that you're making lines and not line segments. Line segment looks like this. Line looks like this. So you have to make these arrows definitely on both sides. This shows that the line is extending in both directions, okay? And even what I have done is that I have pulled these lines also in either directions, okay? Reason being, it's not a line segment, okay, whose length is fixed. It's got infinite length. It's infinitely extending in either directions. That's why. Okay, so you can write the equation numbers also here. Like this is equation 1, x plus 3y equal to 6. This is equation number 2, 2x minus 3y equal to 12. Do write the scale. 1 centimeter or 2 centimeter is equal to 1 unit on both axes. And now graphically you can see that this is a pair of intersecting lines. Intersecting lines meet at how many points? Only one, and hence the solution corresponding to that is called unique. And this is that point, 6, 0. So the solution is, first of all, the point is what? The point is 6, 0. So the solution is what? This is x and this is y. So solution is x equal to 6 and y equal to 0. So it's very simple. Okay, the main thing is how you plot it, which we've done already. Now you just need to figure out, what kind of lines they are. Just look for the points of contact and you're done. Let's have this example number 5. So this is equation 1 and this is my equation number 2. Now here some of you might be getting intimidated by the look of second equation. Well, I am also, because here we are having fractions. We just hate fractions in algebra. So what we can do is, I can simplify it, okay? What if I multiply this by 5 by 3? Then I'll be able to get rid of these fractions. See how? So I'm doing second equation into 5 by 3, okay? And now I will get 3 into 5 by 3x minus 24 by 5 into 5 by 3y plus 3 by 5 into 5 by 3 is equal to 0 into 5 by 3, which is 0. Now make whatever cancellations you can, okay, and don't be surprised because now you will get 5x minus 8y plus 1 equal to 0. Call it equation number 3, but it's same as equation number 1. How is it? This is a case of coinciding lines. Without even plotting, you can make it out, because this is a dependent pair of linear equations. So the formation of this equation depends on the existence of this equation. When we multiply this equation by 5 by 3, or no, in this case 3 by 5, we get equation number 2. So multiplication of first equation, that is the original equation, by 3 by 5 is giving us this second equation. So this is a dependent pair of linear equations, which we also call coinciding, but still we'll verify it graphically, okay? Because the question asks you to do so graphically. So here you can just write 1 or 3, doesn't matter. Okay, you can write both actually. So just do this. So let me take some points over here. So if I take x to be 0, will it work? It won't, because I'll get a decimal value. So in this case, if I take x as 3, you will get y as 2. If I take x as minus 5, I'll get minus 3. And now you realize that no matter which point you take on the x-axis, ranging from minus 8 to 8, you'll always end up getting a fractional or a decimal value for y. But I told you that you have to avoid it under all circumstances, but here it is inevitable. So we'll make use of a fraction which is still easier to plot. So if I take x as minus 1, I get y as minus 1 by 2. It's still easy to plot. I'll show you how. So first let me plot x3 by 2, label it. Then minus 5 comma minus 3, which is over here. And then we have minus 1 by 2. So this is for minus 1. On the y-axis, just make it half. You'll be having small square boxes within these boxes also on your graph sheet, I'm sure. So you can just count it. It will be probably the 5th box, okay? So this is minus 1 comma minus 1 by 2. So it's easy only, but still, okay? Here it was inevitable, that's why we took an easier case, okay? Now just make use of a ruler, join it, and you get this. You can write this equation number 1 and 3. You can write the full equations also. And do mention the scale on the top right hand corner. So we were having 2 equations, but it appears to be just one straight line. So obviously it is coinciding lines, which always render us how many solutions? Infinitely many solutions. So that is the answer. Okay. Moving on to example 6, the last example in this topic. So there's this girl Champa, very fond of shopping, I tell you. So she went to a sale and she decided to buy herself some pants and skirts. We don't know the exact number of what she bought. So let's say that the number of skirts that she bought were X and the number of pants that she bought were Y. Now let's look at the conditions which have been mentioned in this particular question. The number of skirts, which means X, is 2 less than twice the number of pants. Twice the number of pants means 2y, 2 less means minus 2. So the first equation would be x is equal to 2y minus 2, but let me pull out this 2y over here. By default it's plus over here, so it will become minus over there. So I'll have x minus 2y equal to minus 2. Let's call this equation number 1. Then look at the second condition here, that the number of skirts x, and here we have 4 times the number of pants, which is 4y. It is 4 less. That means 4y minus 4. So that's how you can also frame your second equation. X is equal to 4y minus 4. In a similar way, you can rearrange and get x minus 4y is equal to minus 4. Now you need to do it graphically. So let's make 2 boxes. Let's make 2 Cadbury chocolates over here for equations 1 and 2. And slice them with 1 horizontal line and 3 vertical lines. Write x and y here, x and y here. Now refer to equation number 1, take some values of x and get the values of y. So if I take x as 0, I'll get y as 1. Okay, if I take x as 2, I'll get y as 2. If I take x as 4, I'll get 4 minus 2y as minus 2, minus 2y as minus 6, and y as 3. Let's focus on equation number 2 now. So if I take x as 0, I'll get y as 1 once again. If I take x as 4, I get y as 2. If I take x as 8, I'll get 8 minus 4y equal to minus 4. Minus 4y becomes minus 12 and y becomes 3. Let's plot these points. So 0, 1, label it also. Then 2, 2, 4, 3. So this is for equation number 1. Then we have 0, 1, the common point. Then we have 4, 2, is this point, 8 comma 3, which is this point. Okay, make use of a ruler, join it by some straight lines. Okay, here what you need to do now is that write the equation numbers. Okay, so you can write like this is 2, 2, 4, 3. So this is equation number 1. You can write the full equation also. This is equation number 2. Mention the scale also. What does this case tell you? We are getting a case like this. What are these? These are intersecting lines. At how many points do they meet? Only at one. What is that point of contact? That point of contact is 0, 1. Like here also we got a common point, you can see. So point of contact is 0, 1, and that is only the unique solution. So in this case, that unique solution would be x equal to 0, y equal to 1, which means how many pants did she buy? She bought 1 pant, and x is equal to 0 means 0 skirts. And that is your answer. Okay, so the next time you go on a shopping spree, try making use of your algebraic concept.